Thank you so much for the presentation. And yeah, I'm from the Autonomous University of Hidalgo State in Mexico. And well, today I'm going to present this work. This work is a little difficult because this situation of the pandemic, so I have to try to obtain different results. But well, all the results will be presented tonight. So thank you for inviting me, and it's a big honor to be here. Okay, so we're going to start with this presentation. All right. Before talking about, I'm sorry. Wait me for a moment. Okay, we are going to start with this. Okay. Why determination of methanol in drinks is so important? Well, methanol, as chemists, we know that methanol is a harmful primary alcohol. So in the alcoholic drinks industry, we know that methanol modifies the organoleptic properties of drinks. This is an important topic. Why methanol is important to detect. The other part is the regulatory laws of health ministries in this country. So manufacturers has to present a specific concentration of methanol in the alcoholic drinks. If you don't establish this concentration, your product is not suitable for drink in the population. The other part is the health importance. The presence of methanol in alcoholic drinks is very harmful. A dose of 15 milliliters of methanol may cause death. And methanol, when it is inside of the body, reacts with several enzymes, and these enzymes generates formic acid as former product. So this formic acid causes acidosis and blindness inside our body. And the first sign of methanol intoxication in our body is to see this kind of black dots in our visions. So this is very important to detect before drink alcoholic drinks. Okay. Then, how can we detect methanol? How the chemists can we detect methanol? Well, the important part of detecting methanol is gas chromatography. Gas chromatography is the cornerstone of methanol detection. However, gas chromatography is expensive and time-consuming. Therefore, we are looking for new alternative methods or more less expensive methods to detect methanol in alcoholic drinks. The solution, there are a lot of solutions. However, we propose the electrochemical methods as a principal solution to resolve this problem. We know that the electrochemical detection of methanol is based on redox reaction that occurs on the electrode surface. We have the molecule, we apply a specific potential, and with this potential, the molecule get oxidized. That's the principle of the electrochemical sensors. However, if we use commercial electrodes, there is no selective oxidation of methanol. In this case, we oxidize methanol and ethanol in the both cases. So this is very bad for analytical method because the electrochemical signal of both alcohols emerge and cannot be distinguished with this technique. So a specific solution for this problem of selectivity is to use modified electrodes, in this case with MOF, to obtain a selective response to methanol. With these modified electrodes, we can propose a new alternative to detect methanol in alcoholic drinks. Well, in this case, or in this project, we use metalloorganic frameworks as active materials on modified electrodes. Why we use these materials, or what is the selection of these materials to use in modified electrodes? Well, the first part of this selection of these materials is because metallic centers on MOF, the metallic part of the MOF, has a redox properties in alkali media. This redox property generates oxidation pair that is useful on the selective oxidation of molecules. The other part is the selective absorption of specific molecules too. In this case, we can capture some molecules, for example, a methanol. We can capture selectively the methanol, and then we can electrocute that methanol and generate an electrochemical signal. So this is the important part of the MOFs, because we have a selective electrocatalysis. And this selective electrocatalysis is useful in non-enzymatic electrochemical sensors. For example, there is a lot of investigation about non-enzymatic electrochemical sensors for glucose, for hydrogen peroxide, and other biomolecules. The other part is they use some fuels. At the present, there is a lot of investigation too in water splitting, methanol direct cell fuels, and other application. And the most recent part is the energy storage. Well, methanol electrocatalysis with MOF can be explained using a proposed mechanism called the Fleischmann mechanism. In this mechanism, we have the MOF initially in alkali media. The MOF reacts with the alkali media to yield a high oxidation state of this MOF. These species are called hydroxide species. Then this species reacts with the analyte to produce, in this case, the oxidation products or the corresponding oxidation products. For example, in the case of methanol, the methanol reacts with these high oxidation species, and then we produce, for example, formaldehyde or formic acid. And then this layer can be represented with cobalt, with nickel, copper, zinc, and iron. These transition metals has this compartment in alkali media. So this is an important part for the modification of electrode with modes. There is a lot of discussion about the change in the coordination environment. However, at the present, there is no clear idea about how the MOF or the MOF structure is changed when it's in alkali media and then when reacts with the analyte. So the changes in coordination environment are still clear. Well, the scope of this project is to develop an electrochemical sensor based on a copper MOF for the selective electrochemical detection of methanol in alcoholic twins. Well, we start with the synthesis of this MOF. This MOF is the copper BTC. It's a very important MOF in the literature. And well, first we have the micrograph of the MOF. In this case, this image was obtained by SEM, and we can see different shapes of the crystal that we obtain of these materials. The shapes varies, and we can see octahedrons structures and irregular forms in these crystals. And then we evaluate these crystals by powder diffraction X-ray, and then we compare our results with other reports about this MOF, and well, we can see this comparison of the X-ray patterns, and the X-ray patterns are very similar. So in conclusion, we obtained this MOF exactly. Then this characterized MOF was incorporated in this case in carbon-based electrodes. These carbon-based electrodes are elaborated by hand. This is an artisanal method. We combine, in this case, graphite, the MOF, mineral oil, and then we obtain this paste, and this paste is packing in a plastic tube, and then we place an electric contact, and then we have the electrode. So in this part of the elaboration of the electrode, we consider a different proportion of the MOF. In this case, we consider the 7%, the 15%, and the 30%. And this is the electrochemical response of our electrode. in this part, we evaluate first the electrode containing 50% of the MOF, and we can see an increase of the electrochemical response. In this case, the electrochemical response that we are looking is this at 1.4, and we assign this signal, this oxidation signal, to the redox pair of copper 2 plus to copper 3 plus that is presented in alkali media. And this oxidation peak increase when we add a methanol in the mixture, in the solution we are evaluating. So this is the first part that indicates that there is an electrocatalytic response to methanol. Then we evaluate this response at the different proportion of the MOF, and we see variation of the response. For example, when we have 7% of the MOF in the electrode, the response is low. However, when we have 50% of the MOF in the electrode, the response is very high. And this response decreases when we add at 30% of the MOF. This is because our MOF is not a conductive material. I mean, there is no electron conductivity in the MOF. And as a result, we have decrease of the current intensity. Well, consider the optimal parameters. In this case, the 50% is the parameter that generates high a high current density. We consider this parameter, and then we evaluate the electrolyte concentration. As mentioned before, we use sodium hydroxide, alkali media. However, there is different concentration of sodium hydroxide in this experiment, and then we evaluate how this concentration affects the electrochemical response to methanol. The best response was obtained at this concentration, and I have an error here. This concentration was 0.1 molar, the red one. And this concentration was used as a best electrolyte concentration to obtain the best electrochemical response to methanol. And then we evaluate the methanol concentration effect. When we add different methanol concentrations in our electrolyte and in our electrochemical system, we can see an increase of the current intensity, and this increase presents a linear tendency. So this linear tendency indicates us that this electrode could work as an electrochemical sensor for detecting methanol. However, we have to establish a new method for detecting methanol. If we use cyclic voltammetry, as we can see here, we have different interference during the measurements. So we have to use another technique or more effective technique, electrochemical technique, to detect methanol. Then we evaluate differential pulse voltammetry. For this part, we generate an experimental design, a Box-Benken design, evaluating different variables of the differential pulse voltammetry. And then we obtain this response. These are our optimized parameters, and then we use these optimized parameters to generate an effective electrochemical method to detect methanol in alcoholic drinks. With these optimized parameters and using these optimized parameters in differential pulse voltammetry, we evaluate again the effect of the methanol concentration. And again, we find this linear tendency. So we continue with this compartment, and then we the next part is to evaluate this compartment now in methanol ethanol mixtures. I mean, when we have an alcoholic drinks, obviously we have the different percentages of ethanol in the mixtures. So this part is to simulate how our electrode could act when we have these mixtures of ethanol and methanol. And we can see a specific difference. For example, when we have, for example, in this part, the 30% of ethanol and 0.1 millimolar of methanol in the mixture, we don't have any difference. However, when we change the ethanol concentration in the mixture, for example, in 50% or 10% or 5%, we can see a specific difference, a clear difference when the methanol is present in the mixture. So this compartment is was very exciting for me, because this indicates that our electrode effectively works selectively, has selectivity to methanol, even in the presence of ethanol. So this is a very exciting part. Then with these results, we select a specific ethanol concentration to evaluate, and then we add different methanol concentration at that ethanol concentration. In this case, we use 10% of ethanol in the mixture, and then we add different concentration of ethanol. And again, we had this linear response. That was very exciting to obtain this linear response, because there is a selective oxidation of methanol in our system. So this part is very exciting to present. Then, due to the linear response that we obtain, then we decide to move to another proof, another experiments, and then we decide to evaluate in this case real samples. Real samples, for example, we use a cane liquor. In Mexico, we'll call aguardiente, and mezcal. I think all Americans know the mezcal. It's a very popular drink in the United States. So we use these samples, and we dilute these samples to the 10%. Mezcal was diluted to a very low percent of ethanol, because the response was very high. So the response generates interference, and that's the case we dilute to this percentage. All right. So to analyze these dilute samples, we analyze by the standard addition method. I mean, we have the real sample, and then we add different methanol concentrations to the sample, and then detect using different equations, we generate the real concentration of methanol. In this case, the real concentration of methanol is this value for cane liquor, and for mezcal is this value. According to the Mexican regulatory authorities, this value is overpass the limit of methanol in the drink. So be careful if you consume mezcal. All right, then the next part was to compare our results obtained by differential pulse voltammetry versus gas chromatography. In this case, we built calibration curve to detect the methanol in our real samples. And these are the results. The results are very similar to the obtained with our electrode. So this indicates that we have very reliable electrode. Then the next part was to evaluate by statistical analysis. We use the student t-t's comparison of two means. In this case, we have, well, in this part, we have the results with the differential pulse voltammetry using our electrode. And this part is the results obtained with gas chromatography. As you can see, there is no difference between the both results. Well, the next part was to use the t-test to compare this statistically. And well, the result is that there is no significant difference between both methods. This is what very exciting, because at the present time we can propose a new alternative to detect methanols. It could replace the gas chromatography even. All right, our future direction is to use this electrode in small devices. There is a lot of do-it-yourself devices compatible with our electrodes and can be applied to detecting methanol in situ. I mean, we can use these devices. For example, we go to the bar, for example, and we don't know if that drink we are drinking is tainted. we could use this kind of electrochemical sensors to detect if our drink has methanol. And well, this is the first direction. We have to build this kind of electrochemical sensors. And well, maybe in some years we have this kind of devices in our smartphones. Concluding remarks, our MOF displayed a selective electrocatalytic activity toward methanol, even in the presence of ethanol. The selectivity is probably originated by the effect of the pore size in the MOF, and maybe is to the kind of metallic center in our MOF. High percentage of ethanol, there was an interference of signal that affect the detection of methanol. However, if we dilute the samples or the real samples, we don't present this interference. And finally, the MOF composite that we use in the electrode has the potential application in small electrochemical devices and can we use directly in situ to detect methanol. And we finished with this, and this is my acknowledge. I want to thank to my research group and another university that helped us with the characterization of the MOF, and Consejo Nacional de Ciencia y Tecnología for the support and the scholarships and the funding source. And well, we finish with this, and thank you for your attention.
All right, fantastic. Let me get you, if you don't mind, just go ahead and lead the talk up, because I think some of the questions are about,
All right.
or at least related to certain parts of it, I think. So let's see. So the first one here, okay, so I may have missed this. This was a question I had, so my apologies if I did. Is there a reason you chose the copper specifically? Is it more selective than the other cations, or is it just one that you just sort of started with?
We use copper because it was our first option. I mean, we didn't have in that time the salts of the other metals, and the only salt we have in that moment was copper.
Hey, fair enough.
So
no judgment. I've done that before. No judgment.
Yes. So that was the first part. No? At the present time, we are evaluating other MOF. I'm working with the nickel MOF using this ligand, because there is the carboxylic benzene acid, and I'm planning to use cobalt too.
Okay.
However, I have not much time to do a lot of experiments due to the pandemic situation.
Sure.
However, we are evaluating other metals in this electrode.
Okay, that'll be really interesting to see.
The response is very different. For example, when we use nickel, the electrochemical response is very high compared with copper.
Oh.
However, at the present, we don't know if we have selectivity.
Sure.
I'm not doing that experiments at the present. I'm working with that.
Okay.
But I think copper is the best selection for the MOF.
Okay. Interesting. Okay, so this was, so you kind of talked, well, you talked about having the mix of ethanol and methanol.
Yes.
But we had a question here. Is it possible to have ethanol get trapped as a guest in the MOF? And if so, does that cause issues with the methanol sensing?
Probably. There are several computational studies in this part. We were reviewing this part, and we found that methanol is more suitable to be trapped in the MOF pores in comparison with ethanol, because ethanol, the molecule is bigger than ethanol. So I think this is a very important part, because we can absorb selectively the methanol, and probably ethanol is not affecting our response in that part. The thing, or the problem with this is that ethanol could react with our MOF during the electrocatalysis and can be oxidized. However, the oxidation of this ethanol is not is not higher than the methanol oxidation.
Okay. So I'll skip to a question that was asked later on that's kind of related to this, because you're talking about the pore sizes. Are there any other linkers that you could use in the copper MOFs to try and change your limit of detection or your substrate of interest?
Yes, there's a lot of linkers. For example, we can use the bicarboxylate benzene acid.
Mm-hmm.
It is demonstrated that bicarboxylate benzene acid is more conductive than the benzene tricarboxylic acid. However, I don't have that linker in my laboratory,
Okay.
and that's the first problem that I have, because I don't have these reagents to be used for the MOF synthesis. But it could be interesting to evaluate it in the future and generate a new MOF with this linker, and maybe evaluate it in methanol electroxidation.
I got you. Yeah, that's a good point. So let's see. Okay, so when you showed you had the figure with the methanol and the ethanol mixed together. At least you noted that as you got to higher concentrations of ethanol, there was a smaller and smaller difference. Does that mean that you would want to have, so like in terms like taking this and making it like the applications that you talked about, you have a little handheld device and you want to test something, do you need to have a reference, or is that something that you could do beforehand? Like how would you know, how are you going to know that there's methanol in your in whatever you're measuring, especially if you're dealing with that small step, you know what I mean?
Yes, technically, we don't have or we don't need any reference, because methanol is generating an oxidation signal, as I present in the graphs. For example, that we have to know is maybe if the alcoholic drinks, or what kind of alcoholic drinks we have to evaluate. For example, when we evaluate non-distilled alcoholic drinks, there is a probability to have more methanol in the mixer in comparison when we evaluate, for example, the no-distilled, the distilled drinks. The concentration of methanol could be lower. However, even if this concentration is lower, we can obtain this signal. This signal is characteristic in our system. And this signal, for example, we evaluate the ethanol only, and we don't have this signal when ethanol is present. It's only for methanol. So I think the selectivity is helping us to detecting methanol in low concentrations.
Okay, I got you. Can you talk a little bit more about how you determined the actual methanol amount? So you had the mezcal and the slightly higher ethanol concentration, the one that's about 10%, and you showed you added methanol to it and you got a linear regression off of that. Is that how you calculated the actual methanol amount? I didn't quite follow that part.
I'm sorry, I didn't understand you. My internet is.
Can you pull the presentation back up real quick?
All right, let me share my screen again. Let me go to that part. This one, right?
It was the one. It was towards the end.
This one.
Go forward too.
This.
Forward. Yeah, this one. Okay. So you have.
All right.
So I see. So you have like the linear regressions for the mezcal. Let's say. How did you, based off that linear regression, how did you calculate the actual methanol amount?
All right, the real concentration of methanol in the mezcal, right?
Exactly. Yeah.
Okay. Well, we use a standard addition method. We use several equations based of the question of the graph,
Mm-hmm.
and with this equation we initially calculate this methanol concentration in millimolar,
Okay.
expressed in millimolar,
Mm-hmm.
and then to express the methanol concentration, the real methanol concentration, we
Okay.
consider the dilution factor. I mean, it's not the same to have 10% of ethanol in the mixture, and or we have the real ethanol percent in the mixture. So we consider that dilution factor,
Okay.
and we multiply the results by the dilution factor to obtain this real result.
Okay. All right. So you backed out what? So you calculated your concentration in your diluted sample, backed out what you started
Yes.
with, and then just did the conversion.
Yeah, we
Okay.
have to carry out the conversions.
Gotcha. Okay. All right. I got you now. That makes good sense. That's a really cool way to do it. So the last question I've got here, and anybody in the chat that wants to ask more, it's not a hard end, so feel free to ask any more that you've got. How good is the stability of this electrocatalyst? Have you done any
All right, that's a pretty cool question.
Yeah.
All right, the stability, for example, we have good stability in aqueous system, in water, for example. However, when we increase the pH of the alkalyte, or of the electrolyte, for example, when we use sodium hydroxide in 1.0 molar concentrations, the MOF gets dissolved.
Okay.
So the MOF is not stable at that concentration, a high concentration of sodium hydroxide.
Okay.
So that's the reason that we evaluate this part of the pH of the electrolyte concentration, because we present this problem when we evaluate that. So see, yeah, that's a very cool question. The other part we didn't evaluate in acid media. Probably in acid media the MOF gets dissolved too, because we can't get soluble salts of the copper.
That makes sense. So if you pick a pH where the MOF doesn't dissolve, can you have you done any repeated testing in the stable region? So just making sure that you can run the same test over and over again, or is it it works a couple of times and then you get
we can use this electrode several times. The advantages of use carbon-based electrode is that they are cheap, and in this case of the carbon-based electrode, we can renew the surface of the electrode in each experiment. For example, when we use plastic carbon electrodes, in this case you have to cast the MOF in the electrode surface. If you do several experiments, you have to repeat this procedure. In the case of the carbon-based electrode, you don't have to do that. You only renew the surface by pressing the paste in the electrode, and you clean that surface in a white paper, and that's all. That's the only thing you have to do.
Okay, I mean that's great. That's a good, easy way to do it.
Yeah,
that's very cool. Okay, and you said you're planning, right now you guys are trying other cations, other metals, to see if any of them maybe have better response or something like that. Correct?
Yeah, the idea is to optimize the response to methanol by evaluating different metal centers in the MOF. However, I mentioned before, due to the pandemic situation,
it makes it hard.
Yes, has limited our presence in the laboratory, so it has been a little bit difficult to evaluate this part.
Sure, absolutely. No, I understand that very well.
Yes,
that makes it very difficult.
I was planning to finish that part specifically in this year. However, the goals were not reached this year.
It's a lofty goal, but I'm sure you'll get some interesting results out of it. So I think it'll be worth doing.
Thank you so much.
Sure. Yeah, like I said, I mean this is really cool stuff. So hopefully you'll come back once you have the rest of your results. You can tell us about that too. That'd be really great.
Yes, I would like to present it in a future. I think maybe in 3 months, probably, I will have the results.
That would be fantastic. Then that'd be good. So we will we get to look forward to a follow-up talk.
I have some results. For example, I have crystallized the MOF, and we evaluate the crystals by diffractions, and we have the molecular structure, and we are evaluating the response to methanol. And at the present, we have a good response to methanol with a high chlorine intensity. However, I think there are few results, and they don't have to be present at the moment.
Sure, that's fine. That's fine. We'll get to look forward to it in the future. That'll be great.
Yes.
I think that looks like that's all the questions we've got. So if I can get you to hang around for just 1 minute after we're done, we'll talk real briefly, and then I'll let you go. But in the meantime, thank you again for a fantastic talk.
Thanks to you. It was. I get nervous during the speaking, but I tried to do my best.
Hey, you did a fantastic job. Like I said,
thank you so much. Thank you so much.
You got like I said, you're doing some really interesting stuff. So that's really cool. So thank you again, Antonio, for your talk. Thank you to everybody for coming out. We will be back next week. We have let's see, Dr. Jorge Almodovar. From the University of Arkansas.
All right.
So I hope you will all come back out next week. We actually have I think we have a presenter every week, except for the 17th and the holidays. So Thanksgiving, Christmas, and the New Year. So
yes, I know.
Lots of talks lined up. I'm excited, and it's going to be a good rest of the year. But in the meantime, again, thank you everybody for coming out, and please have a great weekend. And we will see you again next week. Be safe and have a good one. And we'll see you all then. Bye, everybody.